Hello everyone, this is audio recording for visually impaired students from Pradeep's Physical Chemistry. The distribution law. Introduction. Definition of the distribution law. It is observed that when a solid or a liquid is added to a mixture of two immiscible liquids in both of which it is soluble, example iodine to a mixture of carbon disulfide and water, or succinic acid to a mixture of ether and water, it distributes itself between the two liquids in such a manner that the ratio of concentrations of the substance in the two liquids is always constant at constant temperature. These observations were made by Berthelot and Jungfish in 1872. However, it was pointed out by Nernst in 1891 that the ratio of the concentration is constant only when the solute has the same molecular weight, that is, the molecular state, in both the solvents. Hence, the generalization was put in a proper form by Nernst and is called Nernst distribution law. It states as follows: a solid or liquid distribute itself between the two immiscible solvents in such a way that the ratio of the concentration of the solute in the two solvents is constant at constant temperature, independent of the presence any other molecular species, provided that the solute has the same molecular state in both the solvents. Thus, if a solute X distributes itself between the two immiscible solvents A and B, then if X remains in the same molecular state in both the solvents, we will have concentration of X in solvent A upon concentration of X in solvent B is equals to C1 by C2 is equals to K, a constant. The constant K is called distribution coefficient or partition coefficient. To test the validity of the law, that is to verify the law experimentally, different amounts of a solution of iodine may be added to mixtures of water and carbon tetrachloride taken in different bottles. These are then shaken and allowed to stand. A known volume of each layer is pipetted out and then titrated against hyposolution to find out the concentration of iodine. Similar experiments may be performed with other solutes and immiscible solvents. A few results of some earlier experiments are given in the table on the next page. It is important to note that it is the ratio of the concentration which matters and not the ratio of the total weights of the solute present in two solvents. Hence, the same units of concentration must be used for each solvent. Conditions under which distribution law is valid. The distribution law is valid only if the following conditions are satisfied. Number 1. The temperature must remain constant throughout the experiment. Number 2. The two liquid solvents should be mutually immiscible. Number 3. The amount of the solute added should be small, that is, solution should be dilute. This is essential because in certain cases the solute added affects the mutual solubility of the solvents. 4. The solute must have the same molecular state in both the solvents, that is, it should not undergo association or dissociation in any of the solvents or combination with any of the solvents. Thus, the law is not valid for the distribution of benzoic acid between water and benzene because it has been observed that in benzene, benzoic acid undergoes association to form dimers, that is, it exists as C6H5COOH whole twice. Similarly, the law is not valid for the distribution of an electrolyte like HCl acid between water and a non-polar solvent like benzene, CS2, CCl4, etc. because the electrolytes undergo dissociation in water. Thermodynamic derivation of the distribution law. The thermodynamic derivation of the distribution law is based upon the principle if there are two phases in equilibrium, that is, two immiscible solvents containing the same solute dissolved in them, the chemical potential of a substance present in them must be same in both the phases. From thermodynamics, we know that the chemical potential mu of a substance is given by mu is equals to mu naught plus RT ln A, where mu naught is standard chemical potential, A is the activity of the substance solute in the solution. Thus, for the solute in liquid A, we have mu A is equals to mu naught A plus RT ln A. Similarly, for the solute in liquid B, we have mu B is equals to mu naught B plus RT ln AB. But as already stated, since the liquids A and B are in equilibrium, mu A is equals to mu B. Then mu naught A plus RT ln AA is equals to mu naught B plus RT ln AB, or RT ln AA minus RT ln AB is equals to mu naught B minus mu naught A. The chemical potential is defined as the partial molar free energy, that is the change in free energy per mole change of composition of that component in the solution, keeping the composition of all other components constant. The activity of a substance in the solution is its effective concentration. Then ln AA upon AB is equals to mu naught B minus mu naught A upon RT. Further, at a given temperature, mu naught A and mu naught B are constant for given substance in the particular solvents. Hence, at constant temperature, we have from equation 4 ln AA upon AB is equals to constant, and therefore AA upon AB is equals to constant. This is the exact expression for the distribution law. However, if the solutions are dilute, the activities are equal to the concentration, so that the expression is modified to Ca upon Cb is equals to constant, which is the original form of distribution law. Change in the molecular state and distribution law. As mentioned earlier, Nernst was the first person to point out that the distribution law in the form C1 by C2 is equals to constant is applicable only if the solute remains in the same molecular state in both the solvents. That is, it does not undergo association or dissociation in any of the solvents or combination with any of the solvents. If, however, such changes takes place in any of the solvents, then the law cannot be applied to the total concentration of the solute in two phases, but only to the concentration of identical molecular species in two phases. In each of these cases, the distribution law equation is modified as discussed below for a few simple examples. Case 1. When the solute undergoes association in one of the solvents, suppose the solute X remains in normal molecular state in the phase 1, but N molecules of it associate to form complex molecule Xn in phase 2. Then the following two equilibrium will exist simultaneously as shown in figure 5.2. Equation 1. X is in equilibrium with X in phase 1 and phase 2. Second, Nx is in equilibrium with Xn in same phase 2. Suppose the total concentration of the solute X in phase 1 is equals to C1 and the total concentration of solute X in phase 2 is equals to C2. Also suppose alpha is the degree of association of the solute in phase 2. Then concentration of the associated molecule in phase 2, that is Xn, is equals to 1 by n C2 alpha, and concentration of unassociated molecules in phase 2 is equals to 1 minus alpha C2. Applying the distribution law to equilibrium 1, we get concentration of solute X in phase 1 upon concentration of normal molecules of X in phase 2 is equals to constant. C1 upon 1 minus alpha C2 is equals to constant. Again, applying the law of chemical equilibrium to equilibrium 2, we get concentration of associated molecules in phase 2 upon concentration of normal molecules in phase 2 की power n is equals to constant 1 by n C2 alpha upon 1 minus f alpha C2 की power n is equals to constant. C2 alpha upon 1 minus alpha C2 की power n is equals to constant. Taking the nth root, we get C2 alpha nth root upon 1 minus alpha C2 is equals to constant. Dividing equation 1 by equation 2, we get C1 upon C2 alpha nth root is equals to constant. When the molecules in the phase 2 are almost completely associated, that is alpha is equals to 1, therefore C1 upon C2 nth root is equals to constant. Alternatively, the same result may be obtained in a simple manner as follows. Suppose concentration of solute X in phase 1 is equals to C1, concentration of the associated molecules in phase 2 is equals to C2, and concentration of simple molecules in phase 2 is equals to C3. Applying the distribution law to equilibrium 1, we get C1 by C3 is equals to constant. Again, applying the law of chemical equilibrium to equilibrium 2, we get C2 upon C3 की power n is equals to constant. Taking the nth root of both sides, we get C2 nth root upon C3 is equals to constant. Dividing equation 3 by 4, we get C1 upon C2 nth root is equals to constant, which is the same as derived above. Thus, in such cases, when the solute undergo association in one of the solvents, the constant value for the partition coefficient is obtained not for the ratio C1 by C2 but for the ratio C1 upon C2 nth root. This relationship has been confirmed by studying the distribution of benzoic acid between water and benzene, the acid existing mainly as associated molecule C6H5COOH twice in benzene solution. The following results were obtained. Thus, where the ratio C1 by C2 shows great variation, the ratio C1 upon under root C2 is nearly constant. The formula C1 upon C2 nth root is K is commonly used for finding the value of n, that is extent of complexity of the solute molecules in one of the solvents. This is done by finding out the concentration C1 and C2 of the solute in the two solvents in a number of experiments. The value of n is then calculated as explained later in section 11.5.2. Case 2. When the solute undergoes dissociation in one of the solvents. As before, suppose the solute X dissolved in the phase 1 without any change in the molecular state but undergoes dissociation into Y, Z, etc. in phase 2. Then as shown in figure 5.4, the following two equilibria will be set up. 1. X in phase 1 is in equilibrium with X in phase 2. Number 2. X is in equilibrium with Y plus Z in the same phase 2. Suppose total concentration of solute X in phase 1 is equals to C1 and total concentration of solute X in phase 2 is equals to C2. Also suppose the degree of dissociation of the solute in the phase 2 is alpha. Then concentration of undissociated molecule in phase 2 is equals to 1 minus alpha C2. Applying the distribution law to equilibrium 1, we get C1 upon 1 minus alpha into C2 is equals to K, constant called partition coefficient. Note, it is obvious that if the solute undergoes dissociation in phase 1 with degree of dissociation alpha but remains normal in phase 2, then the formula obtained will be C1 into 1 minus alpha upon C2 is equals to K. Similarly, if the solute undergoes dissociation in both the phases with degree dissociation alpha in each, then the formula will be C1 into 1 minus alpha upon C2 into 1 minus alpha is equals to K. From the above expression, the degree of dissociation alpha can be calculated. Case 3. When the solute undergoes a combination with one of the solvents. Suppose the solute X remains in the normal molecular state in phase 1, but one molecule of it combines with n molecules of the solvent has to form the compound molecules X and S in phase 2. Then as shown in figure 5.5, the following two equilibria will be established. 1. X in phase 1 is in equilibrium with X in phase 2. Number 2. X plus NS is in equilibrium with X and S in same phase 2. Suppose concentration of solute X in phase 1 is equals to C1, concentration of normal molecules in phase 2 is equals to C2, concentration of solvent molecules in phase 2 is Cs, and concentration of the compound molecules in phase 2 is Cc. Applying the distribution law to equilibrium 1, we get C1 by C2 is equals to K, the distribution coefficient. Again, applying the law of chemical equilibrium to equilibrium 2, we get Cc upon C2 into Cs की power n is equals to K1 equilibrium constant. Since the solvent in phase 2 is present in excess, its concentration Cs remains almost constant in spite of combination with the solute X, particularly if the solute is added in small quantity, that is the solution is dilute. Thus Cs की power n is constant, and so the equation 6 becomes Cc by C2 is equals to K1, Cs की power n is equals to K2, another constant. Adding 1 to both sides, 1 plus Cc by C2 is equals to 1 plus K2, or C2 plus Cc upon C2 is equals to 1 plus K2. Dividing equation 5 by equation 7, we get C1 by C2 into C2 upon C2 plus Cc is equals to K1 upon 1 plus K2, or C1 upon C2 plus Cc is equals to K upon 1 plus K2 is equals to K3, another constant. But C2 plus Cc is the total concentration of the normal as well as the solvated molecules of the solute X in phase 2. Thus, the above equation in fact implies that total concentration of solute X in phase 1 upon total concentration of the solute X in phase 2 is equals to constant. Hence, we conclude that when the solute enters into chemical combination with one of the solvents, there is no modification of the distribution law equation except that numerical value of the partition constant is changed. Applications of distribution law. The distribution law has been applied to the study of problems of both theoretical and practical interest, a few of which are briefly discussed below. In calculation of the solubility of a solute in solvent, when the two immiscible solvents are in contact with each other and the solute is added in such a large excess that saturated solutions are formed, then the concentration of the solution at this stage will be equal to their solubilities. Assuming that distribution law is applicable for such concentrations, we will have C1 by C2 is equals to S1 by S2 is equals to K, where concentration C1 is equals to S1 is the solubility of the solute in solvent 1, and concentration C2 is equals to S2 is the solubility of the solute in solvent 2. Thus, knowing the distribution coefficient K, the solubility of the solute in one of the solvents that in the other can be calculated. In studying the extent of association or dissociation of the solute in a solvent, we have already seen that when a solute undergoes association in one of the solvents in which its total concentration is C2 and has a normal molecular state in the second solvent in which its concentration is C1, then distribution law formula is modified to C1 upon C2 under nth root is equals to k, the distribution coefficient. From this formula, the value of n can be calculated either by hit and trial method or by logarithm method as explained below. Number 1. Hit and trial method. The values of C1 and C2 obtained in different experiments are put in the equation. C1 upon C2 nth root is equals to k, then putting n is equals to 2, 3, 4 etc. one by one. The values of k are calculated in each case. The number which gives constant value for k is the correct value for n. Number 2. Logarithmic method. The formula for finding n is C1 upon C2 nth root is equals to k, or C1 upon C2 की power 1 by n is equals to k, and then C1 is equals to C2 की power 1 by n into k. Taking logarithm of both sides, we get log C1 is equals to 1 by n log C2 plus log k. For two sets of values C1, C2 and C1 dash, C2 dash, we have log C1 is equals to 1 by n log C2 plus log k. Log C1 dash is equals to 1 by n log C2 dash plus log k. Subtracting equation 2 from equation 1, we get log C1 minus log C1 dash is equals to 1 by n log C2 minus log C2 dash, or n is equals to log C2 minus log C2 dash upon log C1 minus log C1 dash. Hence, n can be calculated. Similarly, when a solute undergoes dissociation in one of the solvents in which its total concentration is C2 and has the same normal molecular state in the second solvent in which its concentration is C1, then we have C1 upon C2 into 1 minus alpha is equals to k, the distribution coefficient. From this formula, the degree of dissociation alpha can be easily calculated. In predicting distribution indicators, it has been seen that iodine distributes itself between CS2 and water with a distribution coefficient equal to 400 towards CS2. Thus, if a weak solution of iodine is to be estimated, then a few drops of CS2 or CCl4 may be added to the solution. As a result, a considerable amount of iodine will pass into CS2 layer and give it a deep violet color. Now the solution may be titrated against hyposolution till the violet color in CS2 layer disappears. Thus, iodine acts as a distribution indicator in this case. In the study of chemical equilibria leading to the formation of complex ions, example Ki plus I2 is in equilibrium with Ki3, Kbr plus Br2 in equilibrium with Kbr3, CuSO4 plus 4NH3 in equilibrium with CuNH3 4SO4. Distribution law helps to determine the equilibrium constant for any of the above equilibrium reactions and hence to establish the formula of complex ion on the basis of constancy in the value of the equilibrium constant. As an example, let us consider the first equilibrium reaction. The study of this equilibrium involves the following steps. A solution of iodine in CS2 is shaken with water to find out the distribution coefficient of iodine between water and CS2. Number 2. A solution of iodine in CS2 of known concentration is shaken with Ki solution also of known concentration. Number 3. After the distribution of iodine is completely between the two layers, the concentration of iodine left in the CS2 layer is determined by titrating against standard hyposolution. The result is then calculated as follows. Suppose that initial concentration of iodine in CS2 is equals to A moles per liter. Initial concentration of Ki solution B moles per liter. Concentration of I2 left in CS2 layer after distribution is equals to C moles per liter. Distribution coefficient of I2 between water and CS2 is equals to K. As iodine reacts with Ki, the total concentration of iodine, that is free plus combined, in the aqueous layer is much higher than if no Ki were present. Obviously, total concentration of I2, that is free plus combined in aqueous layer, is equals to initial concentration of I2 in CS2 minus concentration of I2 left in CS2 layer is equals to A minus C moles per liter. Concentration of free I2 in aqueous layer can be calculated by applying distribution law, that is, concentration of free I2 in aqueous layer upon concentration of I2 in CS2 layer is equals to K. But concentration of I2 in CS2 layer is equals to C moles per liter. Concentration of free I2 in aqueous layer is equals to Kc mole per liter. Amount of I2 that has combined with Ki is equals to A minus C minus Kc moles per liter, that is D moles per liter. Now according to the reaction Ki plus I2 equilibrium with Ki3, number of moles of I2 combined is equals to number of moles of Ki combined, that is equal to number of moles Ki3 formed. Concentration of Ki3 in the aqueous layer is equals to D moles per liter. Concentration of Ki in aqueous layer is equals to B minus T moles per liter. Concentration of I2 in aqueous layer is equals to Kc moles per liter. Substituting these values in the equilibrium law expression, that is K dash is equals to concentration of Ki3 upon concentration of Ki into concentration of I2, the equilibrium constant K dash can be calculated. Starting with different initial concentration of iodine and Ki solution, the value of K dash is determined in each case. A fair constancy in the value of K dash confirms the formula of the complex Ki3 or that of the complex sign I3 negative. In the process of extraction. The process of extraction is of great importance both in the laboratory and industry. In the laboratory, the process is often used for the removal of dissolved substance from an aqueous solution with the help of organic solvents like ether, chloroform, carbon tetrachloride or benzene. In the industry, the process is used to remove the impurities from the product. Basically, the process involves shaking of the aqueous solution of the substance with an organic solvent which is immiscible with water, but in which the substance to be extracted is soluble. After shaking, the mixture is allowed to stand. Most of the substances passes into the organic layer from which the former can be separated out by distilling of the organic solvent. However, in order that the process of extraction may be more effective and efficient, the following two conditions must be fulfilled. Number 1. The value of the distribution coefficient of the substance between water and the extracting solvent should be greater in favor of the extracting solvent. It is sometimes possible to increase the distribution coefficient artificially by making the substance less soluble in the aqueous phase. This can be done by adding some substance which depresses the electrolytic dissociation of the compound being extracted. If a strong inorganic acid HCl is added to the solution, the hydrogen ion concentration is increased and the ionization of organic acid is reduced because of common ion effect. In the solution, there will be greater amount of the undissociated acid and hence the amount extracted will be greater. Similarly, an organic base can be best extracted in the presence of a strong inorganic base. The addition of salts also usually lowers the solubility of an organic compound in water. Number 2. The whole of extracting solvent available should not be used in one lot, but it should be used in maximum number of installments. Then this factor increase the efficiency of extraction can be seen as follows. Suppose X gram of the substance are present in 1 liter of the aqueous solution. Also suppose 1 liter of ether is available as the extracting solvent and that the distribution coefficient of the substance between ether and water is 2. Now if the whole of the ether is used in one lot and X gram with the amount of the substance extracted into ether, then we will have concentration in ether upon concentration is H2O is equals to X upon 1000 upon X minus X upon 1000 is equals to 2. Small x is equals to 0.67 x, or thus only 67% of total amount will be extracted in this case. Again, suppose the whole of the ether is used in 2 installments, each of 500 cc. After shaking first installment of 500 cc, suppose x1 gram of the substance passes into the ether layer, then clearly x1 by 500 upon x minus x1 by 1000 is equals to 2 and x1 is equals to 0.5x. Thus 50% of total amount is extracted out in this operation. Therefore, the amount of the substance left and extracted is 1 by 2x. That is 25% of the total substance passes into ether layer in this operation. Therefore, total amount of the substance extracted is equals to 50 plus 25 is equals to 75%. Thus, when 1 liter of ether is used in 2 equal installments, the percentage extraction increases from 66.7 to 75. Similarly, it can be seen that 1 liter of ether is used in 4 equal installments. The extraction increased further to 93.75. A general formula can be derived which gives the amount of the substance left unextracted after a definite number of operations. Suppose W gram of the substance is present in V ml of the solution made in solvent A. Also suppose that V ml of the extracting solvent B is used each time and K is the distribution coefficient of the substance between the solvents A and B. Now, if W1 gram be the amount of the substance left unextracted in solvent A after the first operation, then concentration in A upon concentration is B is equals to K, that is W1 by V upon W minus W1 by V is equals to K, or K into W minus W1 by V is equals to W1 by V, or W1 is equals to Kv upon V plus Kv into W. Again, after the second operation, if W2 gram be the amount of the substance left unextracted in solvent A, so that the amount extracted is W1 minus W2 gram, then W2 by V upon W1 minus W2 by V is equals to K, or W2 is equals to Kv upon V plus Kv square into W. In general, after the nth operation, the amount of the substance left unextracted will be Wn is equals to Kv upon V plus Kv ki power n into W. In order that the extraction may be most efficient, clearly Wn should be smallest possible. This can be shown only if the factor Kv upon V plus Kv ki power n is as small as possible. Now in this factor, the denominator V plus Kv is greater than the denominator Kv. Therefore, Kv upon V plus Kv is less than 1. Hence, the above factor will be smallest possible when n is the largest possible. So, it follows that multi-step extraction is more economically than single-step extraction. Further, from the above solution, it may be seen that Wn can never be equal to 0. Howsoever large n may be, in other words, extraction can never be complete howsoever large number of extraction may be carried out. Otherwise also it is clear that every time the substance left distributes itself between the two solvents, some quantity howsoever small must be left unextracted. Note: for the purpose of numerical problems, it must be remembered that K is the distribution coefficient of the substance between the solvent A already present and the extracting solvent B. If K is given for the distribution of the substances between solvents B and A, the reciprocal of this value should be used in the above equation. The principle of multi-step extraction holds good for washing the precipitates, whereby the impurities distribute itself between the liquid and precipitate. Further, in Park's process for desilverization of lead also, use is made of the principle of extraction. Silver is more soluble in zinc than in lead. Zinc is immiscible with molten lead. Thus, when zinc is added to argentiferous lead, a large quantity of silver goes into molten zinc layer, leaving the little silver in the molten lead layer. Because the distribution coefficient of silver between zinc and lead is 300 at 880 degrees Celsius, zinc contains silver forms the upper layer. Thus, by repeating the process, almost total quantity of silver can be extracted from argentiferous lead. In the determination of degree of hydrolysis, let us first study some terms and expressions related to salt hydrolysis. Hydrolysis constant. The general equation of the hydrolysis of a salt Ba may be written as Ba plus H2O gives Ha plus BOH. Applying the law of chemical equilibrium, we get Ha into BOH upon Ba into H2 is equals to K, the equilibrium constant. Since water is present in very large excess in the aqueous solution, its concentration H2O may be regarded as constant, so that we have HaBOH upon B is equals to KH2O is equals to KH, where KH is the hydrolysis constant. Since Ha and BOH represent the molar concentration of the free acid and free base, produced, and Ba represent the molar concentration of the unhydrolyzed salt, and the above expression for the hydrolysis constant may be written in a more general way as Kh is equals to free acid into free base upon unhydrolyzed salt's concentration. Degree of hydrolysis. The degree of hydrolysis of a salt is defined as the fraction of total salt which is hydrolyzed. For example, if in a solution of aniline hydrochloride 90% of the salt is hydrolyzed into aniline and hydrochloric acid, the degree of hydrolysis is 0.9 or may be expressed in percentage 90%. It is usually represented by symbol H. H is equals to number of moles of the salt hydrolyzed upon total number of moles of the salt taken. Expression for the degree of hydrolysis for solution of different types of salts. As salts of strong acid and base do not undergo hydrolysis, therefore to talk of KH or H of such salts is meaningless. The cases of the other three types of salts are discussed below. Salts of weak acids and strong base. Representing salt by Ba as usual, the hydrolysis may be represented as follows: Ba plus H2O in equilibrium with BOH plus HA. BOH is strong and HA is weak. Or then A negative plus H2 in equilibrium with OH negative plus HA. That is in case of anionic hydrolysis. Suppose the original concentration of the salt in the solution is C moles per liter and H is its degree of hydrolysis at this concentration. Then we have A negative plus H2O in equilibrium with OH negative plus HA. Original concentration at equilibrium C 0 molar concentration at equilibrium C into 1 minus H CH. The hydrolysis constant will therefore be given by Kh is equals to OH negative HA upon A negative, that is CH square upon 1 minus H. If H is very small as compared to 1, then 1 minus H is nearly equal to 1. So the above expression becomes CH square is equals to KH and H is equals to KH by C under the root. H is in proportional to 1 by C under the root. Thus the degree of hydrolysis of a salt of a weak acid and a strong base is inversely proportional to the square root of its molar concentration. Number 2. Salts of strong acid and weak base. For such a salt Ba, the hydrolysis may be represented as Ba plus H2O in equilibrium with BOH plus HA, or B positive plus H2O give in equilibrium with BOH plus H positive. That is in a case of cation hydrolysis. Proceeding as in earlier case, we get the same relationship H is equals to KH by C under the root. Number 3. Salt of weak acid and weak base. Representing the salt Ba as before, we have Ba plus H2O in equilibrium with BOH plus HA, or B positive plus A negative plus H2O in equilibrium with BOH plus HA. That is, it involves both anion hydrolysis as well as cation hydrolysis. In this case, we have B positive plus A negative plus H2O in equilibrium with BOH plus HA. Original concentration C0, concentration at equilibrium C into 1 minus H, C into 1 minus H, CH. KH is equals to H square upon 1 minus H ka whole square. Hence, the relationship between KH and H does not involve C. Thus, the degree of hydrolysis of such a salt is independent of the concentration of the solution. If H is very small in comparison to 1, we can take 1 minus H nearly equal to 1. So, the equation becomes KH is equals to H square and H is equals to under the root KH. Determination of degree of hydrolysis by the application of distribution law. Suppose it is required to determine the degree of hydrolysis of aniline hydrochloride, which is a salt of weak base and a strong acid. The method consists of 2 steps. Number 1. Determination of the hydrolysis constant. Aniline hydrochloride is hydrolyzed as C6H5NH3 positive OH negative plus HCl. The hydrolysis constant will therefore be given by KH is equals to free aniline into free HCl acid upon unhydrolyzed salt. Thus, to get the value of KH, the aim is to find the molar concentration of free aniline, free HCl acid and the unhydrolyzed salt in an aqueous solution of aniline hydrochloride. This is done by shaking aqueous solution of aniline hydrochloride of known concentration with benzene. As a result, the free aniline distributes itself between the two solvents, that is water and benzene, whereas HCl acid and the unhydrolyzed salt remain in the aqueous layer only as shown in figure. A. Calculation of concentration of free aniline in the aqueous layer. For this purpose, the concentration of aniline present in the benzene layer is found by taking a known volume of this layer, evaporating off the benzene, and finding weight of aniline left. Having known the concentration of aniline in the benzene layer that in the aqueous layer can be calculated. The distribution coefficient of aniline between water and benzene is known, which can be found by a separate experiment. B. Calculation of concentration of free HCl produced. From the hydrolysis equation, it is clear that the number of moles of the salt hydrolyzed is equals to total number of moles of aniline produced or free HCl produced, which has already been calculated in step B above. Hence, knowing the initial number of moles of the salt taken, the number of moles of the salt unhydrolyzed can be calculated. Further, knowing the volume of the aqueous layer, the concentration of the unhydrolyzed salt can be calculated. Number 3. Calculation of degree of hydrolysis. Knowing the hydrolysis constant Kh, the degree of hydrolysis of a solution of aniline hydrochloride having concentration C moles per liter can be directly from the expression H is equals to Kh by C under the root. Thank you.